In our paper, we propose a new framework for computing bounds on the optimal value of a weighted CSP. Unlike most existing approaches, which optimize a bound over reparametrizations by enforcing different soft-loop consistencies, we show that one can use any constraint propagation method to improve the bound if super-reparametrizations are used. First, we define notation. In a weighted CSP, we have a set of variables v and a common domain D. We also have a set E of variable pairs. We want to find an assignment x maximizing the objective function in equation 1. This function is a sum of unary weight functions and binary weight functions. The weights are real numbers and thus can be also negative. The values of all these functions can be together seen as vector f from Rt, where T is the set of all tuples. In the whole presentation, the structure of all the weighted CSPs will be fixed. Therefore, weighted CSP instances can be identified with these weight vectors f. We will present our approach only for binary weighted CSPs, but it can be easily extended to higher arities. Besides weighted CSP, we will also need the ordinary CSP. Here, the sets V, D, and E are the same as before, and the CSP instance is defined by a set A of allowed tuples from T. As before, since the structure will be the same, we can identify CSP instances with subsets of T. An assignment X is a solution to CSP A if for each variable I, the tuple I xi is allowed, and for each edge ij, the tuple I xi j xj is also allowed. We can define a tractable upper bound Bf on the optimal value of a weighted CSP f, which is defined in equation 3. For any f, the number Bf is greater than or equal to the optimal value of weighted CSP f, which follows from the fact that it sums the maximal weights for each variable and each edge separately. In addition, we say that the tuple ik is active if the weight fik is maximum among all values of fi. Analogously, a binary tuple is active if its weight is maximum among all weights of the corresponding binary weight function. Thus, active tuples are those tuples at which maxima of each individual term of the upper bound are attained. The set of all active tuples for f is denoted by A star f. This set can be seen as a CSP which corresponds to the CSP denoted by bool f in other papers. As an example, consider a weighted CSP with two variables, a single edge between them, and the domain consisting of two labels A and B. In our pictures, variables will be depicted as rectangles, tuples as circles and line segments, and weights are written next to the circles and line segments. Black circles and solid lines represent active tuples, and white circles and dashed lines represent inactive tuples. The upper bound is the sum of maxima of weights for each variable and variable pair. On the right, we show the active tuple CSP A star f, where active tuples are allowed and inactive tuples are forbidden. Weighted CSP f is a reparametrization of weighted CSP g if the value for each assignment in f and g is the same. We can also say that f is equivalent to g, or that f is an equivalence-preserving transformation of g. For a given g, it is natural to minimize the upper bound on its optimal value over its reparametrizations, as shown in equation 4. This is equivalent to the dual of the well-known basic linear programming relaxation of a weighted CSP. Despite this optimization problem has an exponential number of constraints, the set of feasible solutions is just an affine subspace of Rt, so it can be described by a polynomial number of linear equalities. This problem has been studied a lot, and many large-scale algorithms have been developed for it, typically based on block coordinate descent or enforcing soft local consistencies. While reparametrizations are widely known and used, super-reparametrizations have been rarely used explicitly in the literature. A weighted CSP f is a super-reparametrization of weighted CSPG if the objective value for each assignment is greater or equal in F than in G. Again, one can minimize the upper bound over super-reparametrizations as shown in equation 5. Similarly as before, any F which is a super-reparametrization of G yields an upper bound on the optimal value of G. This problem has been already proposed by Komodakis. They showed that the optimal value of this problem is the same as the optimal value of weighted CSPG, which is not surprising, because the problem has an exponential number of linear inequalities. They used this formulation to improve upon the well-known virtual arc consistency algorithm by so-called repairing cycles. We revisited and simplified this approach and generalized it to any constraint propagation method. It can be shown that a feasible vector f is optimal if and only if the active tuple CSP A star f has a solution which has the same value in f and in G. Thus, satisfiability of A star f is necessary but not sufficient for optimality. This will be crucial for our approach in which we use this to obtain improving directions for this linear program. Because we consider only the necessary condition, we obtain only a subset of all possible improving directions. Thus, our approach can be seen as a local search to approximately solve the intractable problem 5. We describe this next in detail. One can show that CSP A star f is unsatisfiable if and only if there exists a vector h such that the bound is lower for f plus h than for f, and the value of each assignment in weighted CSPH is non-negative. We call such vector h a certificate of unsatisfiability for f. A possible approach can be outlined by the following iterative scheme. Given a weighted CSPG, we initially set f to G. If CSP A star f is satisfiable, we terminate. Otherwise, we find a certificate h defined in the theorem above. We update f to f plus h and repeat the iteration. Due to the properties of h, the upper bound bf decreases after each iteration. Moreover, f is a super-reparametrization of G during the whole run of this algorithm because the values of the weighted CSPH are non-negative for each assignment. Consequently, the values of assignments in f increase or stay the same after each iteration. So the optimal value of f also increases or stays the same. Since bf is an upper bound on the optimal value of weighted CSPF, it cannot get below it. Thus, if any time during the algorithm bf becomes equal to the optimal value of weighted CSPF, CSP A star f becomes satisfiable, and we terminate with a possibly non-optimal value of bf. This is because satisfiability of A star f is only necessary but not sufficient for optimality. We illustrate this in the picture on the right. As shown by the blue and green lines, Bg and the optimal value of weighted CSPG do not change since G is only an input. The value Bf, which is shown in red, strictly decreases with each iteration, whereas the optimal value of weighted CSPF non-strictly increases. So far, we assumed that we could decide satisfiability of a CSP in each iteration, but this is not realistic as the CSP is NP-complete. We therefore propose a weaker scheme in which we try to detect unsatisfiability of A star f only in some cases by constraint propagation. In the rest of the presentation, we explain how to compute a certificate H using any constraint propagation algorithm. We will also suggest how to obtain certificates that may prevent the values of the weighted CSPF from increasing significantly. Finally, we will present our experimental results where we used singleton arc consistency as the constraint propagation method. In order to compute such certificates H, we need a new notion. Let A be a CSP and S be a non-empty subset of allowed tuples. An S deactivating direction for A is a weighted CSP D, whose weights are negative for tuples from S, 0 for the remaining allowed tuples, and the values for all assignments are non-negative. One can show that an S deactivating direction for A exists if and only if CSPs A and A-S have the same solution set. This means that we can forbid all tuples from S in A and preserve the solution set of the CSP. This is how the constraint propagation works. For illustration, consider the CSP in this picture. Set S contains only the binary tuple 1A, 2B. If this tuple is forbidden, we obtain CSP A-S shown on the right. Clearly, CSPs A and A-S have the same set of solutions because label B is forbidden for variable 2. As a consequence, there exists an S deactivating direction D, which is shown on the right and has the same structure as A. In the weighted CSP D, the weight of the tuple in S is negative, -1 in particular, and the weights for the remaining allowed tuples of the CSP are 0. Since the weight of the unary tuple 2b is 2, the values of this weighted CSP are non-negative for all assignments. Note that the deactivating direction for A is not unique. One could also choose a different deactivating direction where, for example, the weight in the tuple 2b would be 1 instead of 2. Alternatively, we could choose a different set S, which would also contain the binary tuple 1b, 2b. Recall that a domain wipeout occurs if all tuples in some unary constraint are forbidden. In a similar way, an edge wipeout means that all tuples in some binary constraint are forbidden. Clearly, if there is domain or edge wipeout in some CSP, it is unsatisfiable. Let F be a weighted CSP and D be an S deactivating direction for the CSP A star F. If there is domain or edge wipeout in A star F minus S, then one can show that there exists a step size alpha such that the bound for F plus alpha D improves. In this case, alpha D is the certificate H mentioned earlier. Otherwise, if there is no domain or edge wipeout, we cannot improve the bound, but there exists a step size alpha such that the tuples from S become inactive. This is the motivation for the name deactivating direction. Let us continue with the previous example. Our CSP A is now formed by the active tuples of the weighted CSP F, shown on the left. Also, recall the S deactivating direction D. Setting alpha equal to 1 and summing these weighted CSPs results in the weighted CSP on the right. Because there was no domain or edge wipeout, the bound stays the same, but the tuple in S becomes inactive. Now, recall how a single iteration of a local consistency algorithm works when applied to CSP A. The algorithm finds some set S of allowed tuples so that no tuple from S can be extended to a solution. In other words, CSPs A and A-S have the same solution set. Then, the algorithm forbids these tuples. Additionally, there exists a subset P of all forbidden tuples that already implies that no tuple from S can be extended to a solution. We require our local consistency iteration to provide such a set P, which we call the proof set. Formally, in any CSP A prime where the tuples from P are also forbidden, the tuples from S could also be forbidden without changing the solution set. For example, P can be always trivially set to T minus A. Such sets S and P allow us to construct a deactivating direction D using equation 6, where n is the number of weight functions with at least one tuple in S. If the set P is large, then the values of weighted CSPD will be also large. Therefore, we would like to choose P to be as small as possible. This ensures good behavior of the iteration scheme described earlier. On this slide, we have shown that any constraint propagation method can produce a deactivating direction. As an example, recall singleton arc consistency propagator. Let I be a variable and k be an element of the common domain. If the CSP A, where domain of variable I is restricted to a single element k as empty arc consistency closure, there is no solution of A with xi equal to k, and we can forbid the tuple ik without changing the solution set. So, the set S contains a single tuple ik. The set P could, for example, contain all the forbidden tuples which were necessary to derive the empty arc consistency closure. Let F be a weighted CSP. Consider applying multiple iterations of constraint propagation to the CSP A0, which is the active tuple CSP of F. First, we forbid tuples S0 and obtain CSP A1. Along with this, we store an S0 deactivating direction D0 for A0. Then, we apply constraint propagation on CSP A1 and forbid tuples from set S1. Obtain CSP A2 and store the S1 deactivating direction D1. By continuing in this manner, we can either obtain some CSP AQ+1 with domain or H wipeout, or reach a point where no more tuples can be forbidden by the chosen constraint propagation method. The sequence of such directions can be composed into a single S deactivating direction for A star F, where the set S is the union of all sets S in the sequence. Moreover, if a domain or H wipeout occurred in the last iteration, then the obtained direction D can be used to improve the bound. We now have all building blocks to define our iterative scheme using constraint propagation in detail, applied to a weighted CSP G. Initially, we set F to G. Then, in each iteration, we apply constraint propagation on the active tuple CSP A star F as on the previous slide, and store the intermediate deactivating directions. If domain or H wipeout occurs, we compose the sequence of deactivating directions into a single direction D. In fact, one need not compose the whole sequence, but only its subset that was sufficient to detect unsatisfiability of the CSP. This may prevent the undesirable increase of values of weighted CSP F. Then, we compute a suitable step size alpha and update F, which decreases the bound. And now we repeat the iteration. We terminate when constraint propagation is unable to detect unsatisfiability of A star F and return the best attained bound BF. We evaluated the described scheme on the cost function library, which is publicly available. We implemented two versions of the scheme, differing in the used kind of constraint propagation. In one of them, we used singleton arc consistency, resulting in virtual singleton arc consistency via SuperParametrizations algorithm. In the second one, we used cycle consistency, as in the paper by Komodakis. We compare the proposed approach to other soft local consistency methods which provide a bound on the optimal value. The results are summarized in this table. We can see that the virtual singleton arc consistency method provided the best bounds for most instance groups from the public benchmark and was frequently competitive in the remaining groups. Concerning runtime, each method explores a different trade-off between bound quality and runtime, but the strong soft consistency methods have comparable runtimes on average, except for pseudo-triangles, which are faster but need much more memory. We have proposed a method to compute upper bounds on the maximization version of the weighted CSP. To compute the bound, we formulate the weighted CSP as a linear program with an exponential number of linear inequalities, whose feasible solutions are super-reparametrizations of the input weighted CSP instance. This task is solved by a local search using constraint propagation. We emphasize that, in theory, any constraint propagation method can be used in this approach. As a question for future research, we would like to evaluate if the bounds provided by virtual singleton arc consistency would be beneficial in branch and bound search, or whether approximate solutions could be generated using the super-reparametrized instance. Moreover, our approach could be also useful to solve more weighted CSP instances even without search. Similarly, as the virtual arc consistency algorithm solves our supermodular weighted CSPs without such.